Hi, I'm Bill Kinney, and this is my 88th video in focusing on problem solving to help people for Actuarial Exam 2 on financial math. For the most part, we've been doing problems from the Mathematics of Investment and Credit, 6th edition by Samuel Broverman, and that continues in this video, though we are moving on to Chapter 4 now, which is on bonds. What is a bond? Well, you can think of it as an investment vehicle where you are giving or lending money to a government or a company, and they are paying you back with interest along the way. Actually, it's kind of the reverse situation for a loan that is being paid back with a sinking fund. The periodic interest payments that you would make for a loan are now payments to you, made by the government or company to you, and they're called coupons. And then there's the balloon payment at the end, where with a loan you'd be paying it back, the principal, and with a bond they are paying you the redemption value, which is also called the face or par value of the bond in most situations. So in this problem we're going to be finding prices of various bonds, all redeemable at par at the face value, whatever that is. I should also say that the first part of the problems in chapter 4 from Broverman are not typically labeled with an S. They're not typically old actuarial exam problems, but they're definitely worth learning how to do to help you do problems related to bonds on Actuarial Exam 2. And here's the problem. We're going to be finding prices. How much money would you pay to obtain these bonds that are all redeemable at par? They're all redeemable at the so-called face value of the bond. In each case here, the face value is 100. So at the end of the term, you're going to get 100 back from the government or the company. So we're going to calculate how much you'd pay for those things. We're also going to show how to compare their prices without actually calculating numerical prices. So that'll be kind of interesting. We're going to be able to look at just a formula and think about the formula to help us compare these things. Actually, in terms of calculations, I'm just going to do part A, and then I'm going to let you do parts B, C, and D. I will write down the answers for parts B, C, and D for you, and you can compare how you did. Then the very last thing we'll do will be to write down the formula to compare their prices. But let's think about some important notation and terminology with bonds. The letter capital F represents the face value of the bond, also called the par value. The letter capital C represents the redemption value of the bond, how much you're going to get at the end of the term. And for most situations, very often, C is equal to F. The redemption value typically equals the face value, which is the par value. And that's emphasized here by saying this is redeemable at par. That is the typical case. Bonds historically were printed on paper as a description of the bond terms and included the face value, typically in multiples of $100 or euros or pounds. That was what you're going to get at the end. Oftentimes you can do what's called buy it at a discount. You can pay less than the face value. Sometimes you have to pay at a premium. It depends on what the interest rates are. The letter little r will represent the periodic coupon rate. The coupons, again, are the interest payments that the government or company is giving you periodically. These are very often semi-annual, twice a year. In this problem, when you see this thing, you say it's a 5% bond. That 5% represents the coupon rate as a nominal annual rate. We need to divide it by 2 to get the corresponding effective semi-annual rate, the value of R. The letter lowercase j will represent the periodic yield rate. Once again, typically, the going assumption at least is going to be that that's a semi-annual yield rate. This 7.2% up here represents a nominal annual rate, so we need to divide that by 2 to get the corresponding semi-annual yield rate. The letter N is going to represent the number of periods. And the going assumption, again, is that things are compounded semi-annually, so if that is the case, this is usually or often 2 times the number of years. Okay, that would be the going assumption. Number of half years is what it typically is. P is going to represent the price. All right, let's think about deriving a general formula, and then I'll use that formula for part A. You'll want to pause the video after that point and check the answers that I write down for parts B, C, and D. And then again at the end, we'll do the comparison with just a formula. So here's our timeline, and these times are in half years. There's going to be n of them. So if indeed these are half years, and if n is even, at least n over 2 would be the number of years. Now remember, these coupons are kind of like just periodic interest that you're getting from the government or the company, analogous to you paying interest only on a loan. They're the face value times the periodic coupon rate, F times R. So you have n payments of F times R. And then at the end, at time n, after n periods, you get back the redemption rate C, the redemption value, which again is very often the same as the face value. And from now on, I'm just going to go ahead and call it F. Okay? So that's the basic setup. And I hope it would make sense to you that the price you have to pay at time 0 is going to be the present value of all these payments, with some interest rate. That's going to be J, the periodic yield rate. All right, so if I think of it that way, I've got n payments of F times R. The present value of that payment stream is F times R times AN with interest rate J, being again the periodic interest rate, which is often semi-annual. And then I've got this ending payment of F that needs to be discounted back in time n periods. So I need to multiply by V to the n, where it's really V sub j to the n. V sub j being 1 over 1 plus j. All right, so this is our basic formula for the price, and that would be when you buy the loan from the government or from the company, when they issue the loan, or the bond. There is a bond market where people trade bonds, and they buy bonds that are being sold, and time 0 could be the time you buy the bond, and P would be thought of as being, again, still the present value of the future coupon payments plus the redemption amount, perhaps based on a different yield rate than the original purchaser bought it for. The yield rate can change based on market conditions. It's essentially supply and demand. All right, so let's go ahead and calculate this with a calculator. For part A, let's rewrite down the things in part A. F for all these parts is 100. For part A, the coupon rate is 5% divided by 2. That's the same as part C. For part B and D, it'd be 5.5% divided by 2. This is 0.05 divided by 2 is 0.025, which tells you that F times R is 2.5. What's J? The yield rate for A and C is 7.2 divided by 2. It's 3.6%. For parts B and D, it's 7.7 divided by 2. 0.072 divided by 2 is 0.036. That's what J is. N is the number of periods. It's a 10-year bond. The assumption is it's semi-annual payments, so N is 20. Okay, if it doesn't say semi-annual, that's the going assumption, since so many bonds have semi-annual coupons. All right, so these are the numbers we need to use in this formula. Let's start by calculating AN. Get your calculator out and do this with me. Again, using the memorized formula for AN, I use J of 0.036. I add 1 to it to get 1.036. Take the reciprocal to get V. I need to raise that to the 20th power. Subtract from 1, divide by J, divide by 0.036. AN is about 14.08. Multiply that by F times R, which we already know is 2.5 times 2.5. This first term is about 35.21. That's the present value of all the coupons. at the given yield rate. Store that in register 1. Now take the redemption value, which is the same as the face value, 100, and discount it back to time 0. 1.036, 1 over that is V, raise it to the 20th power, multiply by F, which is 100. 49.30 is this value. Add that to what was stored in register 1, and the answer for part A is about 84.51. All right, now you may want to pause the video and calculate the answers to B, C, and D. And now I will go ahead and write the answers for B, C, and D down here. For B, you should get 84.85. For C, you should have gotten 82.52. And for D, it's 82.97. So those are the answers. Pause the video, write those down if you need to for these things, B, C, and D here. And now let's do the final thing. Let's think about using just a formula where we don't plug numbers in to compare prices. Actually, we will do a little bit of plugging in, so to speak, without calculating the numerical values for those prices. So we want to use the formula, but it's more handy to use a different form of the formula. Let's use the fact that AN at interest rate J is 1 minus Vj to the n over j. In fact, let's solve that equation for Vj to the n. Vj to the nth power. If you first multiply both sides by j, then subtract 1 from both sides before you finally multiply both sides by -1, you get Vj to the n is 1 minus j times an at interest rate j. Let's plug that in here to get a price formula equal to F times R times AN at interest rate J plus F times, in parentheses, this thing. Let me go ahead and distribute right away. F times 1 is F minus F times this is F J AN at interest rate J. Combine these two terms and factor out what's common. There's a common factor of F, there's a common factor of AN, and what's left over is R minus J. That's the formula for the price that I want to use. Let me rewrite it at the top. The price can be thought of as the face value plus the face value times the difference in the periodic coupon rate minus the periodic yield rate divided by the present value of an annuity immediate at interest rate J. All right, let's think about doing some comparisons. What the comparisons I'll do will be comparing A and B, and then A and C, and you can do other comparisons if you like as well. We're just going to think about it here, basically. F is the same in all of these parts. F is 100. So that's constant. This is constant. R minus J, even though R and J both change in these situations, is constant because, look at it here, R is 2.5% minus 3.6%. Divide these things by 2. That's R minus J. 2.5 minus 3.6, negative 1.1%. It's the same using these numbers. 5.5 divided by 2 is 2.75%. This divided by 2 is 3.85%. Let's see. Yeah. 2.75% minus 3.85% is still negative 1.1%. R minus J is negative 0.011 in all these situations. Okay? So that doesn't change. And it is negative. That's something to note here. It didn't have to be negative. Sometimes R could be bigger than J, but here it's negative. So let's now use it. F is constant. F is in both spots here. R minus J is constant. The only thing that changes really is AN between these different scenarios. And that changes based on either J or N changing. So when you compare A and B, n is the same. N is 20 in both cases, 10 times 2. But j changes. J increases as you go from A to B. What does that mean about an? You should know. This is something you should know. Very fundamental. If j goes up, if the interest rate goes up, then the present value goes down. Okay? So B has a higher interest rate for j, so it's got a lower present value for an. However, we are subtracting it. We're subtracting something that's smaller, making P bigger for part B than it is for part A. As you can see, it is. B is bigger than the P for part B is bigger than the P for part A, the price. I'll say that again. B has a bigger j than A, meaning an is smaller, closer to 0 as a positive quantity, but we're subtracting it ultimately because of the negative sign there. So we're subtracting something smaller in B, therefore P is bigger in B. Got that? All right, let's compare A and C. The R and J are the same. In this case, it's the n that changes. N is now 24 in part C instead of 20. For the fixed j, an does increase with n, excuse me. As n increases, n increases. So an is bigger for part C than it is for part A. However, again, we're subtracting it because of the negative sign there. So therefore, the answer for part C is actually smaller than it is for part A, as you see it is down here. Say that again, okay? This increases as n increases, an does, but we're subtracting, making P decrease as n increases in the situation. So C is smaller than it is for A. And that's the end of this video.